Welcome, my name is Terry Stoll, and this is Programming Chaos, a channel devoted to fun and interesting programming projects to help you hone your programming skills. Today's project is a one-dimensional cellular automata. So you can see it here. It creates all sorts of interesting, colorful patterns, and there is an infinite amount of variety that you can create with it. Good for creating all sorts of different procedurally generated textures. And the basic idea, which you can sort of see here with larger cells, is we have a row of cells, and each cell is in a particular state represented by its color. And then we just have update rules. So a given cell will change its states based on its current state and its neighboring states. So this is a cellular automata. It's similar to, for example, Conway's Game of Life, which is a two-dimensional cellular automata. And I have a video on that linked here. This is a one-dimensional cellular automata. So really, we just have a single row of states that keeps updating. But to make these interesting patterns, when we update a row, we draw the new row below it. And so each new row represents the next set of states, and that's how we get these, as I say, interesting patterns. So before we start programming this, we should take a slightly closer look at exactly the details. So here I have a row of cells in different states, so state 0 and state 1, and state 0 is colored white and state 1 is colored black. These are sort of arbitrary, but standard for computer programming, of course, to use zeros and ones. And the question is, how do I update these states? So what are the rules that I use? So for example, for this state here, state 1, what should it change to be? And it depends both on its current state and at least some of its neighboring states. So I'll say for now, the states to the left and the right. And for that, we just need a rule set. Here I've come up with some arbitrary rules. For this particular state that I'm interested in, we have 0, 1, 0. So I come over here, 0, 1, 0 becomes a 0. So there we go. This state in the next time step is going to be a 0 based on its neighbors. And then I can look at this state whose neighbors are 1 and 1. So 1, 0, 1. 1, 0, 1 becomes a 1. There we go. And this state is 0, 1, 1. So 0, 1, 1 becomes a 0. So that's all you do to update the states. You have a rule that says look up what a state is plus its neighbors and what should it be replaced with. For the states on the end that don't have a neighbor, there's a couple of options. You can assume a default value like a 0 and a 0, but that can result in some weird artifact. So instead, what's often done is you just treat this as wrapped around. So the neighbor for this state is the state on the other end and vice versa. For a basic two-state cellular automata, right? Two states, 0 and 1, with a neighborhood of one cell on the left and one cell on the right, these are the rules. And it turns out if you're dealing with this sort of cellular automata, all of these rules can be named. So the idea is starting at the bottom, so starting from my 1, 1, 1, this rule is 0, 1, 1, 1, 0, 0, 1, 0. So it's this column. And if we look at that as a binary number, that gives us 114. So this can be referred to as rule 114. And all of our binary cellular automata with a neighborhood of one cell on either side, has a numbered rule. But we're not limited to two states. We could include more than two states. So we could have a second and a third and a fourth state. We'd probably want to give them different colors. And we're not limited to a neighborhood of just one in either direction. So I could say, well, for this state, I do it for all of them, I want a neighborhood of size 2. And that gives you a much bigger rule set. In fact, if we look at our wider neighborhoods and say the size of the neighborhood is lowercase n, so this would be a neighborhood here, n equal to 2. And if we take the number of states as being capital N, then the total number of rules that we need in our rule set is capital N, the number of states raised to 2n plus the power 2n plus 1. And you can sort of see that. The number of states is capital N. So a given state, like this one, can have n different values. And each of its neighboring states can have n different values. So if my neighborhood is size 2, then I have, and let's say the number of states is 3, then I have 3 states times 3 possible states times 3 possible states times 3 possible states times 3 possible states. So I end up with 3 to the 5th power. And that is the number of rules that I have to have. The possible states over here grows exponentially, and that means the number of rules in my set grows exponentially. In terms of the programming, we can now sort of see how we need to set this up. I need to know how big my neighborhood is. I need to know how many states I want to be using. And then I need to define my rules. And I'll just generate the rules randomly. You can program specific rules if you want, but fun to just play around and see what we can come up with random rules. And just looking at this picture, which is a nice reason to draw it out, this looks a lot like a dictionary, or in Java, a hash map. So I'm going to do pairs of this string, and I'll treat it as characters, in fact, and map it to a specific character. So I'm just going to generate every possible permutation of states and then randomly assign it a corresponding state, and that will become my rule set. With that idea in mind, let's get to the programming. Okay, so here I've got my processing boilerplate, my setup and draw functions that we almost always need when using processing. And the first thing I need for my code is the set of characters that I'm going to be using and the set of states that represents a single row. Next, I need to decide how big each cell is going to be when I draw it on the screen. And I'll start arbitrarily with a cell size of 4. I need to know how many states I want in this model. So the default that I just showed had 2 states, but sort of for programming it, I'll start with 3 states just so that we know we're making a very general version of the program. And similarly, I want to be able to set the neighborhood size. I'll start with a neighborhood of 1. And in this case, 1 means there's 1 neighbor on either side. The other way to look at it would be this is a full neighborhood of 3. But in terms of the coding, it's a little easier to think of it as a neighborhood of 1 on each side. And then it's useful to keep track of the row width. That's simply how wide each row is. And it's also useful to know where each row is on the screen, so I'm going to have a y value that starts at 0. So now I can start defining some of these. I'm going to need 1 character to represent each state, so the size of the character array is equal to the number of states that I have. And I'm going to set my characters as starting at 0 but plus 48, which actually means that my first character representing a state will be the character 0. Not the integer 0, but the character 0. That's the plus 48, and if you look it up on an ASCII table, 48 should be 0, assuming I got that right. And then my next character will be a 1, and my next character will be a 2, and so forth. That doesn't really matter. You could use A, B, C if you wanted. I'm just figure I might as well start with 0, 1, 2. It is entirely possible to write this code where instead of using characters, we're actually using integers. And my row is, instead of a set of states represented by characters, it's a set of states represented by integers. The trade-off there is twofold. So 1, characters take up less space, so this is going to use a little bit less memory, which might help to run faster. I haven't noticed a big difference, but it's something to think about. Also, when I build my hash map, my rules are going to be a string, and so if I was doing this as integers, I would have to turn those integers into characters to build the string anyway. So I figure I might as well go ahead and make them characters right from the start. So this is my set of characters that I'll be using for my states. Next, I need to figure out what my row width is. And that's simply the width of the window divided by the cell size. And that'll be useful just as I go across the rows. And now I can say that a given row is an array of characters that is long as the row width. So the next thing I want to do is fill in that row with just random states. And here's how that works. I go through the entire row width, and for each element of the row, I'm going to pick a random character out of my set of characters. Now, to make sure that this works, I want to display that row. It won't do anything interesting yet because I don't have an update, but it's handy to be able to display it. So I want to display the row at the current Y location. So I'll need my display function. And I just want to go through each cell in the row and display it. So the first thing I need to do is pick a fill color based on the state of that row element. So here we go. As I said, I'm going to take the value of the character, subtract 48 from it. So that shifts me back into the integer range, like a 0. And then I'll multiply by 360 divided by the number of states. And I'm using 360 because I want to use an HSB scale. And I haven't set that up yet, so I'll need to do that as well. But in the meantime, I can draw my rectangles. There we go. So it's I times the cell size. That's the X value. And actually, I'm going to change this. I'm just going to make it Y. So I'm going to have my Y increment by the cell size. And then the size of the rectangle is just the cell size. And now, as I said, I need to change my color mode. So I'm going to use 360 for the hue and 0 to 100 for the saturation and brightness. So I've maxed out the saturation and brightness. I think I'll turn off the stroke as well. And let's see if that will work. So there we go. All I have is one row across the top, but you can see several different colors. In fact, there should be green, blue, and red because I have my 3 states. So one row drawn. Now I need to do the updates. And so the first thing I need to do the updates is to define my rule set. And for that, I need my hash map. So first I'm going to define it. And I'm going to be mapping from a string to a character. And one thing you might notice is here I'm not using char, that's the primitive data type, which is not allowed to be part of a hash map. Instead, we have to use the full character class. And this is just going to be a new hash map. Again, mapping from a string to a character. And then I want to create a function to generate that hash map for me. So as part of my setup, I'm going to generate the rules. And I'm jumping ahead a little bit. The idea is when I generate the rules, I'm going to do it recursively because I need all possible permutations of states from 0, 0, 0 through, in this case, 2, 2, 2, because I'm dealing with 3 different states. And so I'm going to do this recursively, and I want to start by giving it the empty string, and it's going to build up the correct string recursively. And as it builds up the string, it reduces the length. So when it gets to a length of 0, then it knows that it's done generating the rule. And that'll make a little more sense when I write this function. But what it does mean is I have to pass in an empty string in order to start the recursive process. And so now I can write my generate rules function. So I'm going to be generating a string of length L recursively, and on each recursive step, I will shorten L. And so the base case, the stopping condition for generating this rule is when L gets to be 0. And when L is 0, what that means is I've generated the left-hand part of the rule, my set of states, for example, 0, 0, 0 or 0, 0, 1, and I need to associate with it the new state, which I'm just going to pick randomly. So this looks just like how I generated my random row in the first place. I just, out of the number of states I have, I picked a random character. And in this case, what I'm going to do is take the string that I have and associate it with that random character and add it to my hash map. So in this case, for example, the string 000 is now associated with a random character, maybe it's character 2, and I put that in my hash map, and I have a rule that says if you have 3 zeros, map it to state 2. And then I'm done, so I can return. So that's the stopping condition. If I haven't reached the stopping condition, what I want to do is take one of these characters and add it onto my string. And in fact, I want to do that for each option for the character. And this looks a little odd, but once it's programmed, we can look through it and it should make sense. There we go. So what I'm doing is for each character in my set of characters, or if you want to think about it, for each possible state, I'm going to add that state onto my string, and then I'm going to continue generating the rule with a string that's one shorter. So effectively, the first time I enter this function, L is, say, 3, because I'm starting with 3 states wide. So skip the if and come down to the for loop, and then the first character is character 0. So I stick 0 onto my string, and then I recursively continue to generate that rule. And the second character is 1, so I stick a 1 onto a separate string and start generating the rules. And then my third character is a 2, so I stick a 2 onto a string and I continue generating my rules. So this recursively will generate each possible string. And once the string has gotten down to length 0, that is, I've generated the full length of the string I need, I'll just assign a random character to it. And if you want, it doesn't hurt to print them. So you could put in a print line here to print the rule and print the character R. So the string and the R that it's associated with, and then you can look at what your rule set is because it's being generated randomly. Now I need to actually go into my draw loop and do an update. And I'll just call it an update function that I now need to define. And I'm passing in my current row, which I'll call my old row in the update function. And the first thing I'm going to need is a new row that I put the new states into, right? I can't change my old row as I go. I have to put all of the new values into the new row. Otherwise, I'm going to mess up my calculations. The other things that I'm going to need to know is what character am I currently looking at, or what state am I currently looking at, and I'm going to need to put all of those into a string so that I can look up the proper thing to do in my hash map. So this, again, will make a little more sense once we see all the code. str is going to be the string of the current state plus its neighbors, and x is going to be which state I'm looking at. Based on the current one, I'm going to have to go through all of its neighbors. So I'm going to go through every cell, and I'm going to be figuring out what the new value should be for each cell. So I'm going to figure out what value to put in new R, and I'm going to do that by building up this string based on the neighbors, and then check the hash map for the value. And again, I'll code it and it'll maybe make a little more sense. So here's the basic idea. I is the current cell that I need to update, and dx is the delta from that. So if my neighborhood is size 2, I want to start I minus 2 and go all the way up to I plus 2. And so the current state that I'm interested in, the current cell number, is I plus dx. The only problem with this is it doesn't handle wrapping properly. So if I is 0, the very first cell, and I do I minus 2, I'm going to get an error unless I properly handle wrapping. So let's put that in. There we go. So by adding the row width and then taking the modulus of the row width, that automatically wraps around for me. So x is the current state that I'm looking at. And I'm going to grab the character from the old row and add it onto my string. So this is what I meant about using characters for my states. I can just take the characters and add them onto the string, and I'll build up the string of characters, then I can then look in the hash map. And that turns out to be very easy. The new state value is simply whatever character I get when I look in the hash map with that string. So if my characters were 0, 1, 1, I've built up the string 0, 1, 1 here, and I'm grabbing the correct new value out of the hash map. And then the last thing I need to do is take all of those new values and copy it back into my old row. And I notice while I'm here, I misspelled neighborhood. So let's fix that. There we go. So there we go. That will update my old row with the new values. And the last thing I need to do to get it to display properly is make sure that y is equal to y plus the cell size. So that way, every time I draw a new row, I skip down by one row. So let's see if this all works properly. So there we go. This is, again, an arbitrary rule that was just made up with my generate hash map. And I have 3 states, so 3 different colors. Interestingly, it often looks like more colors because if you have 2 cells side by side, your eye tends to blend them together a little bit, but this should only be 3 colors. And my neighborhood size is 1, so a given cell is updated based on its 2 neighbors. And my cell size is 4, which is fairly large, so you can kind of see the blocks here. And if I run this again, I'm going to get another new rule. So there we go, a completely different rule, a completely different pattern. Run it again, new rule, new pattern. So lots of things you can play with. Not a bad idea if you're interested in just sort of seeing a whole bunch of different rules is to go into the draw loop and set some sort of an if y is larger than the height, generate the rules all over again from scratch. And so in fact, I can go ahead and do that. Let's just take our generate rules and paste that in. So this will give me a new set of rules. Y should be reset to 0 because I want to start over at the top. The other thing that we probably want to do is reset our random row. So I'm going to come up here and restart with a new random row of states. And the one other thing I'm missing to call generate rules, I need my empty string. There we go. And if I did that correctly, nope, there we go. Missing curly bracket to go with the if. Now if I did it correctly, it will fill the screen. And then when it gets to the bottom, it will start over at the top with a new rule. And now we should see yet another rule and another rule and another rule. So each time it's coming up with a new set of replacements, which gives us a new pattern. Okay, so from here, there's lots of things to play with. You can change, for example, the size of the neighborhood. You can change the number of states. You can change the cell size. I left mine pretty big just so this will run quickly. Another option that I like quite a bit, and it's part of what I have on the background in case you were curious about it, is instead of giving each state a unique color, you can say several of the states are just done in black. And so that is, for example, how I got this nice background image. There's actually 3 states here, but 2 of them draw to black and only 1 of them draws to green. And so that's another good effect. Each state doesn't necessarily have to have a unique color. Another thing that you can play with, if you want other things to experiment with, is my starting row across the top is just random. An interesting effect is if you replace that starting row, instead of it being random, you do something that's symmetric. Not all of our rules are symmetric. As you can see, this one is biased sort of in one direction. But if you combine a symmetric starting condition with a symmetric rule, that gives you symmetric patterns, which depending on sort of your own preferences can also be very cool looking. And of course, you can play with the colors. Here, each state gets a unique color. Instead, you could say, I'm going to use one color palette, but each state gets a different level of saturation or a different level of brightness. And so that gives you a whole bunch of different options to play with. So as with most of these projects, this is just the starting point, and I encourage you to see what else you can do with it. Thank you.